Welcome everyone to this second meeting of our webinar series for the project SENERGY NETS. And the title of the meeting today is Pandapipes Meet Synergy Nets. I will be your host for today, and my name is Matteo Filippini, and I'm a project officer for European Heat and Power, who is a European association promoting the sustainable district heating and cooling. And specifically for this project is leading the dissemination and the communication part. Synergy Nets is a project about developing tools to optimize energy networks, also through the integration of renewable resources. And today, specifically, we are delving into the use of panda pipes and how panda pipes can improve calculation and automation of analysis for district heating and for gas systems. Um, Let me go so quickly through our agenda. So first, we will have a brief introduction to Panda tools in general. Then we will go on with the introduction to Panda pipes. And mostly we will be discussing about advantages and functionality overview, so theoretical basics and structure. Then we will proceed through a general intro to Synergy Nets by our project coordinator. And then we will see a use case, so application at a specific Synergy Nets demo site in Milan. We will leave you floors for question at the end of this discussion. So please, you can also use the Q&A box in the chat that you see below of your screen. But please, again, we encourage you to ask us question and to our experts, so we can, be more precise in case you might have any kind of doubts. Let me introduce Erik Prade, our first speaker, who is an engineer and a research assistant at Fraunhofer Institute, who is also collaborating with the University of Kassel. So thank you, Erik, for being here, and I'll leave you the floor.
Okay, thank you very much, Matteo. Yeah, I will give you a short introduction over the Panda tools first, and then, like already mentioned, more specified about Panda pipes. So, the agenda of the introduction, a quick overview, and then a little look at the different tools themselves. So Panda Power, Panda Pipes, Panda Prosumer, and then a short conclusion about the three tools. Yeah, so this webinar is part of a webinar series. We already had a first one in February about Panda Power. Now we are at the webinar about Panda Pipes, and we also have an additional one about Panda Prosumer, the tool that was developed or is developed in this project, and this will be held on the 23rd of April. So what are these Panda tools? Panda Power is, like the name maybe mentions already, is about electrical grids. It's the oldest one of the tools. It was released in 2017 and has now accumulated up to 800,000 downloads, part of which is also automated. For example, if you install Panda Pipes, Panda Power is also installed. So part of these downloads are automated. Panda Pipes is basically the little brother or little sister of Panda Power, and can be used for pipes networks, and was released 3 years later than Panda Power in 2020, and has now up to 66,000 downloads. Yeah, and then we have a Panda Prosumer, which can be used for modeling time series and flexibilities in multi-energy systems. And the open source release is also planned. For now, we have a date set in spring 25, so relatively soon we want to release that. Yeah, about Panda Power, it's an easy to use open source tool to model your power grids or power systems, and also um, make you able to do optimizations or analysis with a higher degree of automation. Um, Key features, basically Panda Power is based on PyPower, so has similar core functionalities, but was further modified and expanded. And because of this open source structure, you can also participate and develop yourself. The main features are power flow calculations, state estimations, topological graph searches, and short circuit calculations according to the IEC standard 60909. And tool itself is implemented in the programming language Python. So because of Python's nature with different packages and libraries, you are able to automate workflows and combine different packages to build your own framework. And you are able to do static and quasi-static calculations with Panda Power. So, for example, do time series simulations over a year and analyze in which seasons or which days you have high loads or low loads on your grid. You're also able to do optimizations, result processing and visualizing, and saving the results to, for example, JSON or CSV or Excel files. Yeah, Panda Power, I think, is a very well-established tool and has been successfully applied to several grid studies with grid operators or cities, and is also used for educational purposes, for example, here at the University of Kassel. And the results have been validated thoroughly with the help of several commonly used proprietary software as well. Okay, pandapipes, like I already said, is basically the little sister of Panda Power, and it's a pipe flow calculation tool, which complements Panda Power in the multi-energy simulations, and can be used for especially district heating and gas systems, but also, for example, water grids are an application. Key features, we basically have a similar structure and also use some functions from Panda Power, so you're able to combine with Panda Power or different Python packages as well. And similar to Panda Power, it's been thoroughly validated. For example, with at least in Germany, it's a very big software, StarNet, and also with Modelica. And you have several components you are able to model, for example, pipes, pumps, valves, but also since about a year, we have developed some district heating components, like, for example, heat consumers or heat exchangers you can use in your simulation. Yeah, and similar to Panda Power, we also have a console application which allows you for these automated evaluations. Like you can write your own scripts or framework around Panda pipes and use it in automated processes. And one big advantage is obviously the open source code. So you have no license costs and can participate in coding and modifying Panda pipes. Yeah, and at the bottom we see some use cases. For example, district heating grids, water supply, or gas distribution. And Panda Prosumer, basically the newest or youngest kid in the family, is used for flexibility modeling in multi-energy distribution grids. And the key features are to enable the generation of time series for these prosumers and model a variety of different prosumers and combine them to implement different control set strategies in your multi-energy system. Some use cases include, for example, the generation of household profiles like electricity and heating demand, but also components for heating and cooling, for example, the usual heating pump or a dry cooler. And obviously, these prosumers can then be used to couple different energy sectors, for example, gas and power or heating and power, and are helpful in modeling the whole coupled multi-energy systems. And yeah, like I already mentioned, we plan this open source release in the next weeks. So the conclusion, we have these three tools in our Panda family. We have Panda Power for power grid calculations. We have Panda Pipes for pipe grid calculations, and Panda Prosumer for modeling the prosumer and time series. And Panda Power was the first tool in this family, and Panda Pipes is based on Panda Power and can be coupled to it. And then Panda Prosumer is the latest edition, which should also enable you to use prosumers to couple the different sectors. Yeah, here are the references for the different slides. And this was the presentation about the different Panda tools. Okay, I think now I'm directly starting with the Panda Pipes presentation, if I'm correct.
Yes, please, Erik, you can go on.
Okay. All right. So, I will now go into detail into Panda Pipes. I want to give a quick overview. Maybe it's doubling with the overview of the Panda family, but I will repeat that, and then we take a little deep dive, not too deep, but we take a little deep dive into the functionality, how you set up a grid, what are the main components you can model in Panda Pipes, how does the structure of the framework itself look, and then a little bit into the calculation side. What equations are we using and how is Panda Pipes calculating your pipe grid? And then at the end, give a little overview of what different type of functionalities we have or use cases. And then I also wanted to show you a quick example of how you would model this or model exemplary grid hands-on in code. Okay, so the overview of Panda Pipes. It's a pipe grid simulation tool for gas, water, and heating grids. We are based on the Panda Power concept, so we use this Pandas Python package, which basically uses a data frame structure to store informations and manipulate it. And for calculation, we use a Newton-Raphson algorithm. And for using this Newton-Raphson algorithm for complicated systems, you basically need to model your equations in matrices, and we use Python's high performance in these matrix calculations to achieve a high performance of Panda Pipes and Panda Power as well. And since it's so closely developed with and from Panda Power, if there are new features available in Panda Power, we also try to incorporate them in Panda Power, in Panda Pipes, and also vice versa. And we have standard type libraries. For example, if you don't want to model your own fluids or gases or pipes with the parameters, You can use our standard type libraries for this, and we also have a few example grids incorporated in pandapipes. What are the advantages of pandapipes? Yeah, like I already said, it's thoroughly validated with, for example, StarNet and Modelica. The model of the grid itself is easy to parameterize. If you want to change something, you can just do it in the console. If you want to uh, model your own type of pipes or other components or fluids, you can also do that if you don't want to use the standard type libraries. And then another advantage of this console applications is that you can build your own framework or code around it and automate your analysis for your grids yourself. Yeah, and obviously we have no license costs. We are open source based, and everyone is encouraged to participate and yeah, include your own developments or come to the community with issues or bugs. And yeah, a big advantage obviously is the Pythonic characteristic that you can combine different packages developed all over the world to your own advantage. Okay, now overview over how you can actually create a net in pandapipes. Um, Here we have a simple example with just one pipe and two junctions. And basically the first step would be to just create an empty network, which is basically the container for all elements and components you add to this grid. Then you add your junctions and pipes. For the junctions, you also specify the nominal pressure and the fluid temperature, which are then in the calculation used as initial values. And then for the pipe, if you are not using standard types, you can define it like this with your own diameter and roughness, but most importantly, like from which junction to which junction is it connecting, and yeah, also define the length. And with these two most important elements like junctions and pipes, we need some boundary conditions for the simulation. So in this case, we create an external grid, which is basically in gas grids a connection to, or for example, a connection to a higher pressure level grid, and can provide yeah, gas at a specified pressure value and temperature value. And then we have another boundary condition, which is a sink, which basically extracts mass flow out of the grid. And yeah, in the next step, you could create your own fluid or create a fluid from the standard type library, in this case, H-gas, which is just a predefined yeah, common gas with its heat capacity and density parameters. And in the next step, you would then call the or do the calculations with calling pipe flow. And the last steps, you can then take a look at your results and, for example, plot them. Yeah, so this was just one way of creating a net. Obviously, you can also, or we have also incorporated into pandapipes a converter, like, for example, from StarNet, if you have your pipe grid not in pandapipes, but already modeled in another software, we have for StarNet a converter, which can then be used to create your pandapipes grid from. And now a short overview over components which can be modeled. So I think the most important components are the junctions and the pipes. Interesting parameters here are H for the calculation of pressure losses between those junctions, and a pipe with the length, diameter, and roughness, who's also relevant for the pressure loss calculation. Then for the fluid, which I just mentioned, we have also the relevant parameters in our standard type library. for example, density, viscosity, and heat capacity. Then, like I already mentioned, we have to define boundary conditions. In this case, we have the external grid, which provides fixed values as a slack node, and the sink, which manipulates the mass in the system. In this case, takes it out. Or we have a source which, in this case, feeds mass into the system. And respective to the different components, we also have results. For example, for the external grid, it's how much mass is provided by the slack node. And for the junctions, we have which pressure is at the specific junction. And if you want to calculate temperature also, what is the temperature at the specific junction? And for the pipe, the main result parameter is the flow velocity. And other additional components include, for example, valves, which can shut off branches or include them, and pumps or compressors, which manipulate the pressure lift between two nodes, or pressure controllers, which set a fixed pressure at a specific node. Yeah. So how do these components get represented in our model? In our framework, we have basically the all overlying object is a pandapipes net in which all other data is stored. And this is basically made up of component tables, which are for each component, we have one pandas data frame, which is where the name comes from. So for example, for source, sink, and junction and pipe, we have one extra data frame, and they are structured in a way where you have for each element a row. And then in the columns, you have the different parameters, for example, for pipe, length, and diameter. And respective to each component table, we also have a result table in which the results for the different elements, again in each row, are stored. And apart from these component tables, we also have the additional information that is stored in, like, for example, standard type tables or options for the pipe flow calculation, like which friction model do you want to use, what tolerance do you set for the Newton-Raphson convergence, what is the ambient temperature for your model, so that the calculation of heat losses from the pipes can be calculated, what are the fluid properties. And then all this data is basically transferred or converted to internal data structure, which then can be accessed for building the matrices and equations used in the calculation sector. Yeah, so what equations are we using in pandapipes? We are basically using the Kirchhoff's laws, so much or very similar to the power system analysis, where we have the junction rule, which basically says the mass flow in and out of a junction should equal 0. And then we have the second Kirchhoff's law, which is the loop rule, which basically says the pressure difference over one loop should equal 0. And for this, we derive equations for each junction and each edge. And you see, for example, in the equations for the edge, we have the height differences, which incorporates this junction heights. Then we have the friction losses, which depend on diameter and the friction parameter of the pipe, and on the friction model you choose. And then we have resistance losses, which you can basically define yourself by this resistance parameter. For example, if you have a pipe with a bending or curve, and you know what these resistance factors, you can incorporate the pressure loss in here. Yeah, and then the last step before the Newton Raphson is basically we want to build the Jacobi matrix to calculate the pressure vector P and velocity vector V. So on the right side, we have our vector for the equations for each element, and the Jacobi matrix is then made up of the partial derivatives for each of these elements. And with these, we are able to calculate our vector we are searching for. So yeah, a quick overview of how the Newton Raphson here is working. We have an initial gas, which basically comes from our initial parameters we set for the junctions and pipes, like the fluid or nominal pressure we set at the junction, for example. And in this initial gas, we then calculate the tangent with the help of the Jacobi matrix. And then we derive with these tangent a new zero, which is then basically our new initial gas. And this Newton-Raphson method is done until we reach the tolerance we wanted to reach. So if it understeps a certain value, which satisfies the user, yeah, we have reached the solution. Yeah, that was it for the calculations. And what are some additional functionalities of pandapipes? So we have the time series calculations, and most of the time used together with it the controllers. So what are time series calculations? Basically, quasi-static calculations where you, for each time step you define, do a static calculation. So for example, the usual application is you have 1 year and you have hourly values for demand, for example, and for each of these demand or for each of these time steps with different demands, you do a calculation to see how to analyze your grid for the different demand situations. And one application here for the controllers could be if you do these time series calculations and you in your time step see your net is not converging, your calculation is not converging, you could use a controller to adapt parameters of your grid to change these. Other applications could obviously be not checking for convergence, but checking for other stuff like, oh, for example, your pressure loss in the grid is too high or your temperature loss is too high. You go into the control step and change your pressure at the slack node or your temperature at the slack node, or maybe also cut off some consumers. So yeah, basically controllers can be used for all sorts of controlling in time series calculations. And then another big functionality is then obviously to plot your net and plot your results. It's very easy to incorporate geodata in pandapipes. You can transfer them from GIS or most other sources and plot your grid according to your junction and pipe geodata, and also include, for example, pressure color maps or pressure loss color maps or velocity color maps to have a very good overview of where issues in your pipe grid occur. Yeah, and now I have brought two examples which we could take a look on. Maybe Matteo, you can give me a quick uh, feedback about the time.
Yes, I think you can go on, Erik.
Okay,
We have time for sure. So please.
okay, I will share my screen.
Yes.
Okay, can you see my screen with creating pandapipes networks? Okay, perfect. Yeah, I have brought two examples. This one is about a pipe grid, gas pipe grid with an external grid and two pipes which go, or one pipe goes to the source, one to a sink. And we also have these two pipes connected with a valve and additional pipes. So we start with importing pandapipes, the package itself, and we create an empty network. In this case, you could also define your fluid here. You don't need to do it in a separate code line. And we let ourselves take a look at what the net actually includes. And we see we have our fluid algas with the different properties, density, viscosity, heat capacity, all already defined. And yeah, the basic components who are already included in the grid, in an empty grid, without defining them, are junctions, pipes, and the external grid. And the next step will then be to use the create functions to create the different elements we want to create, and they will then be stored in the different element tables I showed before in the slides. So in the first step, we would create our junctions we need with the pandapipes create junction command. And like I said, we need these nominal pressure and fluid temperature to set the initial parameters for our calculations. You're also able to give names to the junctions or to all components, and then they can be used for example, mapping or other functionalities. And if we now take a look at what is in net.junction, like in our junction table, we see all these junctions are then listed with the indices, their name, their parameters we defined here. And yeah, one example, like all these functions, all these create functions of pandapipes basically return the index of the element. So for example, for the first junction we created, if we type it out, we get 0 as a return because the first junction has the index 0 in our junction table. And we can also yeah, access this element with a simple pandas syntax and specifying which junction we want to access here. And then we get all parameters specified for this junction. And the same can then be done for the external grid. So also via this create function with the slack parameters here, like which is the pressure it provides and what is the temperature it provides. And then with the same methods, we can also take a look at the component table. Here we have only one element in this component table for this external grid. Yeah, and so you go basically through all these components in your grid you want to have and create for the different elements with these create functions, your different elements. There's also some quality of life functions, so you don't need to create every single line, every single pipe or junction by itself. There are also bulk functions if you want to create multiple of them with one. In this case, you would have to specify like the from junction and to junctions and the other parameters in lists. Like if you want to create 5 pipes, you would have a list of 5 from junctions and 5 to junctions, and also the same with the other parameters. And if we then take a look at what the pipe table looks like, we have then listed these pipes with all their parameters we defined. Yeah, the same can be said for the valves. Here, the deciding parameter is basically if the valve is opened or not. So if this is set to true, the valve is opened and there's a connection. If it's set to false, we have just these two branches separated here. Yeah, and then for the boundary conditions, we have sinks, which are also modeled in a similar way with these create functions, and sources, which are also modeled similar. And yeah, now we are basically done with modeling, and we can take a look like what components do we now have in our grid, and we see, okay, we have these three base components, junction, pipe, and external grid, which were already there in the start, but we added three components that are not standard, and yeah, we see them now occur also in the net, like valve, sink, and source here. And yeah, with this, we are set for doing the calculation, which is then called via pipe flow function. And yeah, you can also specify for which net if you have multiple nets. And this basically does the Newton-Raphson calculation for us. And when this is successful, also when it's not successful, these result tables are created, but when it's successful, they are also filled. And we can take a look again over or into the net object and see, okay, we have added here the result tables like rest junction, rest pipe, and so on for all the components we have. And we can take a look into these tables just by calling them. And we see, okay, for different junctions, pandapipes calculated the pressure values, and yeah, temperature we didn't incorporate in this calculation, so it didn't change. But we see over the pipes, the further away you go from the external grid, you have pressure losses and lower pressure at the junctions. We can do the same for the pipes and see what the calculation did here, and we see different velocities and the different pressure values between the junctions the pipes connect to. Yeah, this was an example for a gas grid. And another quick example I wanted to show is for a heating grid. Here we have an example of a very basic loop with just one consumer, which is here a heat exchanger, and a pump, which is basically providing a pressure lift between the flow and the return flow loop here, and also providing a set temperature at the output of the pump. And for the pipes, we have now a new interesting parameter, which is basically this heat loss coefficient alpha here, which is used to calculate the pressure losses to the surrounding. Yeah, so the structure is very similar, does not change to from gas to water or district heating. We create our empty network. In this case, we have water as a fluid. We again create our junctions. And now the new component I mentioned, we create our circulation pump, which between this return junction we specify here and the flow junction we specify, induces a pressure lift, and at the output induces this yeah, the pressure value set and the temperature value set. In this case, we have 35 degrees. Then for the consumer, in this case, we create a simple heat exchanger, which just takes a specified value of yeah, thermal energy out of the grid. In this case, if this number is positive, it's transferred out of the grid. If it's negative, it's fed into the grid. So you can also model not only heat consumers, but heat producers. Yeah, and then we create our pipes from our specified junctions to the specified junctions. And then, yeah, the important parameter here is heat loss coefficient to calculate how much heat is lost to the surrounding. In this case, we have a surrounding temperature of 283 degrees. And now we can run a pipe flow. The difference you see here is this mode, which basically means we also do a temperature calculation. This sequential mode is that you do the hydraulics first and then the thermal calculations after that. We also have a new mode called bidirectional, where you basically iterate between the two because the thermal results can also influence the hydraulic results. Like the temperature, for example, influences heat capacity and density of the fluid. And yeah, after we do the pipe flow calculations, we can then take a look at the results, and we see not only the pressure changes, but also the temperature. So we have pressure and temperature losses over the pipes. And yeah, we can see the same in the pipe results. And then obviously this is a very simple plot, but basically you can then to better analyze your results, plot your results in all kinds of way because of this Pythonic characteristic. You can use all kinds of plotting packages, for example, matplot, but pandapipes has also some incorporated. And here you can see plotted over the pipe length, the pressure, velocity, and temperature. And as you see, the pressure and temperature drops. But yeah, as we are here working with water as an incompressible fluid, we have the same same velocity. Yes, so that were my examples for pandapipes, and I would now be finished with the presentation.
Thank you so much, Erik. I think it was very insightful and precise in the description, and I hope that people attending had the chance to take notes. And I already saw two questions that we will discuss about during our Q&A session. So please feel free to drop messages. So let me go on and introduce our project coordinator, Renato Luise, who is a researcher at EIFER, and we will drive us through the Synergy Nets projects and give us a bit of a context of the project. So please, Renato, floor is yours.
Thank you, Matteo, and welcome to everyone also from my side. And yes, exactly like Matteo said, my name is Renato Luise and the project coordinator of the SENERGY NETS project. I will try to give you a very quick overview on the project in order that my colleague after Yassan will just explain you how we are going to apply this Panda pipe that Erik just introduced to you to our project. The project, what is about the project and which is the main goal, the main target of the project. How you can read it here. Our goal is to optimize the planning of the district heating and cooling, and finally the distribution with multi-energy system models. And which is our final goal is finally to enhance the flexibility and finally facilitate the sector coupling among different services. The most is between the DSO and TSO, so the distribution system operator and the transmission system operator. How the project is structured. I try to give you a very general overview here. So we have 9 work packages. The final project will consist on 41 deliverables and 12 milestones. The project has started in the 1st September 2022, and it has a length of 4 years for a total budget of roughly 10 million euros. And it answered to a call from the European Commission Horizon AA. As I said here, you can see a bit more in detail the work packages and how they are structured, but just to let you understand how we decided to plan the development of the project. The work package 1 is finally just concerning the management and the coordination of the project, while then we started with work package 2 when we first analyzed all the challenges and we tried to define the use cases and the tool requirements for achieving our goals. Then we went through work package 3, which is mainly concerning the planning of the optimization tool. So you already saw something in the previous presentation. You will see something later and also in the next webinars. And then you can see work package 4, 5, 6. They are basically kind of parallel work packages because they all include the study and the development of use cases and, of course, tool application of our 3 demo sites. Indeed, I will show you later in a map, but finally we have a demo site in Italy, one in Slovenia, and one in France. But it's not all of it, because we also have 2 additional case studies which will not finish with the installation of some model for the optimization, but we will still try to simulate as much as possible, as close to the reality as possible, the existing models. Going through the further work packages, you can see here the work package 7 is more focusing on the value creation from the sister integration. So what we are going to, the added value, the KPIs, we have to first evaluate and then try to understand what are the outputs and how can we quantify the outputs of our work. And then work package 8, as I said, is finally transferability and replicability. So you can think a bit about the scalability. So on some subtask and deliverable work package 8, we will take again the demo cases and we will try to increase the framework of the model, the simulated system, or replicability. So try to understand on which system, which are the most important things that would allow us to have a similar success to the use cases actually analyzed for new use cases, for new demo sites, also including, of course, the 2 case studies that I mentioned before. And finally, the work package 9 is the communication, dissemination, exploitation. So we, of course, like today, we are trying to share as much information as possible to the community in order that our work can be also used by other players. And of course, we are always open to further contribution, to constructive critiques and comments to improve also our work. As I said here, you can just see here a map of all the members of the consortium. Finally, we are 19 partners coming from 8 different European countries, so it's pretty mixed, I would say, colorful, come together of different entities. I try just to give you an overview here. We have 6 research institutes and academia partners. We have also 6 energy supply and services, 2 distribution system operators, 2 software provider, and 3 association and networks. And on top of that, to just conclude the whole, let's say, supply chain, we also try to include a transmission system operator in our advisory board. Concerning the demo site I showed you here before, so as I said, there are 3 of them. They are district heating, and the first 2, so the one in Milan, Italy, and in Ljubljana, Slovenia, are more focusing on a section of the city, so some quarters, while the third, the one in Paris, Illogat-Montparnasse in France, basically it's more focusing on a commercial center and all the different demand for heating and cooling system. Finally, the 2 use cases, one is in Spain, in Cordoba, and the other one in Västerås in Sweden. And I try to give you, for a better overview, all the model that we are actually trying to develop. You have to understand that sometimes the model will stay internally to the company that develop it. But what we are trying to do through the panda tools, let's call all together like that, it's really to try to build open source systems to and make them available for the community. I won't go through all of them here, but basically you can see here in the different column the different case studies and demo sites, and which kind of model are we developing for each of them. I hope I gave you a pretty complete, even though pretty general description of the project. And of course, please do not hesitate in case you have a question to write them down in the Q&A session. And if you are interested in further development of the project, so do not hesitate for following us either on on LinkedIn or, for example, our website. So from my side, it's everything. So thank you very much, and I give you back the floor to Matteo.
Thank you, Renato, for the precious overview of the project. Again, let me take the chance to remind you to follow us on our social media, and please subscribe to the newsletter to always keep updated on our activities. Let's proceed with the last chapter of this webinar, which is going to be about the use case application at SENERGY NETS. So, Hyacinthe, please, floor is yours, and take us through this application at the Milano demo site.
Thank you, Matteo. So yeah, I will tell you about my work in the SENERGY project on the demo site of Milan, and how I applied pandapipes in order to model this use case. So first, I will go through an overview of the distributed network of Milan and the demo site to explain basically how it works. Then how I applied pandapipes in order to create a model of this distributed network. And then I will go into more advanced features of pandapipes that Erik mentioned about the controllers. So I will create a pressure controller in the network and use also the time series simulations that are available in pandapipes. And finally, I will go quickly on what was actually the core of my master thesis subject in the SENERGY project on automatic network extension drawing algorithm that use so pandapipes and what I mentioned before. So this is the distributed network, the demo site of Milan, which is, as you can see, a pretty large distributed network that covers all the eastern part of the city. The operator is A2A. So the company that is also part of the consortium of the project. You can see that on the right side in green, we have the Canavese power plant. That is the main plant that provide heat to the network that is located outside of the city. And then we have a pretty large network of over 50 kilometers of pipes that cover all the eastern part of the city and that provide it to a large number of substations with a total nominal power of 150 megawatts. You can also see that we have larger pipes diameter near the main backbones of the network in order to provide a large mass flow and a large quantity of heat in this part. And in the smaller branches that go to the individual customers, we have smaller pipes diameters, of course. Then I will go through my strategy in order to, from this data that was provided by the operator, create a pandapipes model. So at first I got some topographical representation of the network with a geographic positioning of the different assets of the network. So basically I use GeoPandas, which can easily be converted from a classical GIS software and format with, for example, shapefiles or GeoPackages into this format, which allow me in Python to have the list of all my pipes and the list of all the substations that are in the network with some attributes that represent, for example, the power of the substations or the diameter of the pipes. And then the next step would be to get a topological representation of the network from this, which would represent the coherent connection between the elements. So basically, from this list of pipes and substation, I have to create a graph that represents which pipe is connected to which other pipes or to which substations. So here in this example, in blue, you have all the nodes of the graph that represent the junctions between the pipes, and in red, the junctions that the nodes that represent the substations, and all the edges between these junctions are the pipes of the network. And then I will convert this into the pandapipes network format to calculate the hydraulic and thermal calculation of the network. So for this, I have to remember that actually every edge in my graph represents in related two pipes, because you have also always have the feed, the supply pipes, and the return pipes. So in the first representation with the graph, it's only one, because for the operator, it will be only one path that is designed in the street, for example. They are both at the same location. But for pandapipes, I need to model both because I want actually to model a loop of water in my network. And then I have to include the models from the available pandapipes component library for the heat plant and for the substations, but I will detail that just later. Then I also do some automatic data processing on the data that are available to me. So the first step was to detect some inconsistencies in the data. For example, there are some pipes with diameter of 0, and so I have a program that was able to detect this inconsistency and warn the user when there are some such problem. Also, I can snap in the case of non-matching coordinates. For example, you can see in this case, in red, you have a substation that is not directly connected to the pipes, like the coordinate geographical doesn't match exactly. So I'm able to round the coordinate and be able to snap them to match them, even if there are these small inconsistencies. I will also remove the dangled branches. So there are some cases where you have many pipes in the network that are actually not connecting to anything. Typically, it will be the case if it's here by the operator for maybe a future extension of the network. But in my case, I would like to simplify the network as much as possible. And these pipes are actually not useful for the simulation because I will have a velocity of 0 with no power going through them. So I will also be able in my program to go through the network and to remove all these dangling edges that are not connecting to any client. Also, in the data that are provided and available on the site, I got the nominal diameter of the pipes. But actually, for pandapipes, we need more physical parameters. So I have to convert these nominal diameters into some more precise data on the internal diameter of the pipe, which is the actual parameter that the pandapipes will need in order to calculate the velocity of the water, and as well the insulation thickness that I can use to calculate the heat transfer coefficient that will be used by pandapipes to calculate the heat losses in the pipes. Then how do I model more precisely the heat plant? So the Canavese power plant is actually pretty complex, as I said before. But in pandapipes, I will use one of the many components that are available in the library. In this case, I will choose to use the circulation pump pressure. So this component allow me to set the supply temperature in the supply network. So in this case, I will choose 90 degrees. I can also set the supply pressure here at 8 bars and the pressure delta through the pump that I will set as 3 bars. So basically, this circulation pump pressure will be used as pandapipes as a slack node in the loop. So the main node from which everything else will be calculated when solving the network. And then I model the substation using a new feature in the latest version of Panda Prosumer, which is in Panda pipe, which is a heat consumer. So the heat consumer is one of the components in which you can set the power consumed by the heat consumer. the mass flow and the temperature delta through the heat consumer. But actually, you should set only 2 of these 3 parameters, and pandapipes should be able, if you use the latest bidirectional mode of calculation, to find the third one. So in my case, I will set the power consumed by the consumer to the nominal power of this substation, which is different for every substation. And then I will set the same temperature data of 30 degrees for all these substations. And pandapipes in this calculation will be able to figure out which mass flow through the individual substation will be able to satisfy these 2 constraints. And then I don't really use it, but following this representation on the right of consumer model, I can see that sometimes that may be useful to use some bypass of the substation. For example, in the case where you don't want to have, you want to set a minimal mass flow that go to some part of the network to avoid the very low, very slow velocities, for example. That will result in higher heat losses. And so for this, you can use the flow control elements in which that you can use to set the mass flow that go to this part of the network to a certain value. In this case, I don't use it to just set it to 0 kOhm per second, just to show that using all the components available in pandapipes, we can build a model of the substations that fits the needs that we have in the special case and depending on the data that are available also. And then I will use the Panda Power control module that already Erik shows that how we can use it in pandapipes. But here is a particular case where I will use it in order to control the pressure in the network. So typically I can set, here you have a representation of the evolution of the pressure in a typical distributed network, where the pressure is diminishing in the supply network and again the return network, which means that the customer that is the furthest from the source are actually the lowest pressure ratio that goes through him. And so in my case, I would like to have this minimal substation pressure differential PC of 1 bar. So I want to have at least 1 bar of pressure difference through every substation. And I also want to set the pressure margin, which is the minimal return temperature, return pressure, sorry, at that go back to the pump of 5 bars. And so for this, I create a controller, which is in Python is pretty straightforward by creating a new class to set up this controller in order to control the circulation pump pressure parameters, in this case, the supply pressure and the pressure differential in the pump, in order to meet these constraints. I will also use a time series simulation of pandapipes. So I've got some data that I use to simulate here a typical day of operation of the network. So I will use this load profile in percentage of the nominal power that I apply to every substation in the network. So in this case, I don't have precise data on every substation because there are many of them. So I would use the same profile on all of them, but using the different nominal power of every substation. And here are the results that I got calculated by pandapipes. So you can see the total supply mass flow follow pretty well the real data of the total mass flow so supplied by the Canavese heat plant during this day. On the right, you can see the supply and return temperatures. So in my case, I set the feed temperature of the pump to 90 degrees. So we have a constant value of 90 degrees. But actually, in the real data, we have some variations around this value where the maximum is around 101, the minimum around 80. So we have a few differences in this case. And finally, I will show the pressure. So both the supply pressure and the return pressure at the plants. You can see it follow pretty well. So in the red, we have the feed supply pressure. We have some differences, especially in the case where at the time where the demand is the highest, which shows that there's still some differences in my model of the network and the real data. And I would like to show some of the challenges that may explain these differences. First, it may be due to the data that I've used that in order to create for example, my pressure controller, that may not reflect exactly how the real system is operated. Also, a limitation for now of pandapipes is you can manage only stationary system analysis. So I think it is a work in progress actually for pandapipes to be able to manage transient calculation. But for now, for a pretty large network like this one, calculating only stationary system will result in some differences, especially when you have a large variation of the load during the time, depending on the time step of the calculation. And finally, there may be some difficulty in modeling precisely the heat plant and substations. So the behavior, for example, of the Canavese heat plant is pretty complex because you have different heat production system at the same location. And the modeling of this system in more detail is actually the point of the Panda prosumer library. That will be the point of the next webinar in the 23rd of April. As well, so that we'll be able to couple Panda prosumers that can model more precisely the different systems inside the heat plant, so that the CHP, the heat pump, the storages, etc., and to couple that to pandapipes. Finally, I think I still have a bit more time, or else Matteo can stop me.
No, please go on.
Okay,
Hyacinthe,
so I will say a few words about my master thesis project, actually, which was an automatic network extension drawing algorithm. So I use the same data from Milan network and created a fictional extension of this network to a new neighborhood. So I can see all the points in the red are new substations that I want to connect to the network. And then I have different steps in order to find an optimal way to connect this new neighborhood to the existing network. So the first step will be to create a branch network, as you can see in black, which will use a Pathfinder algorithm to find one way to connect all the customers to the network by following the layout of the streets in Milan. Then I use the ground structure method, which here in green find all the potential pipes that could be added to this first branch network in order to create more connections and potentially some loops in the network that could be added. And then I use a simple mathematical optimization algorithm that will optimize which of these pipes could be actually built or not, and with which diameter, in order to decrease the cost. And so my cost function is actually calculated with pandapipes by calculating what would be the heat losses and the pressure losses in the whole network and evaluating a cost from that. Yeah. Actually, that's all for my part. So thank you everyone for your attention. I give the floor back to Matteo.
Thank you so much, Hyacinthe. I think it was, again, very insightful, this demo site in Milan, also because when things get practical, I think it's easier to understand. So before going on with the Q&A session, I already see that we have 8 questions, so fine. Cool. I would just like to remind you that the next meeting will be, and also the last meeting of the 3 of this webinar series will be on the 23rd of April, and it will be about Panda prosumer, which is not Panda Pro Summer, but still will be so close to summer, hopefully. And you can also see our QR code that can, can get you access to our website and to our social media channels. So I see that Erik and Hyacinthe have already your camera on, so I think I can start with the questions that people drop in the Q&A box. So we'll start in chronological order from Connie. So I'm not an expert in the field, but I'm curious. How does the surface properties, perhaps hydrophobicity of pipe materials, impact heat transport and flow dynamics in district heating systems, especially when dealing with fluids that may contain water? So please, Erik or Hyacinthe, if you have any.
Yeah, I'm not sure if it's like a general question or panda pipe specific, but yeah, of course, the pipe materials impact both heat transport and flow dynamics. And yeah, depending on the main parameters we have for that in panda pipes are the heat transfer coefficient, which is basically encapsulating the heat losses to the surrounding. But if you want to, for example, model the heat stored in the pipe wall or something, we are also working on that. It's like a work in progress. And for the flow dynamics, you can basically define the pipe roughness, which is the main parameter for that, and the pipe diameter, obviously, and then choose from different methods for calculating this pressure losses. Yeah, I think the main one is this Colebrook equation, but yeah, basically there are different ways to do it, and yeah, the pipe materials impact both. Yeah.
Okay, thank you, Erik. I will go on with the second question by Abdul. So, as a PhD student specializing in control engineering, I am researching model predictive control strategies for multi-energy microgrids. During a comparative analysis of simulation tools for thermal hydraulic networks, my team evaluated panda pipes and PIDHN. And we observed that PIDHN demonstrated superior reliability in dynamic simulations, particularly due to its Lagrangian-based pipe modeling and compatibility with MPC workflows. In contrast, panda pipes struggle with convergence in complex networks involving multiple dynamic procedures, in example, heat pumps and GHP units, with varying temporal dynamics. This raises concerns about its suitability for MPC applications, which inherently require robust handling of time-varying states and independencies between components. Given these challenges, would you agree that panda pipes is not well suited for dynamic MPC applications in multi-energy systems, and particularly when modeling networks with heterogeneous producers?
Yeah, so I'm no expert in control strategies or control engineering as well, but we definitely have the challenge of modeling dynamically and with multiple producers on our to-do list. We also figured that out in different projects and SENERGY, that this is something we still would like to develop for especially for district heating, because for gas grids most of the time quasi-static or time series calculations are enough. But for district heating, like multiple sources and dynamic calculations would be nice to have. So we are working on that. Not sure if that completely answers your questions, but yeah, we are aware of the challenge of multiple sources and dynamic simulation.
Please, Hyacinthe, tell me if you have anything to add. Otherwise, I will just go on with the next question.
No, I don't have anything to add.
Super. So, question by Peter. If a network is already defined and a new pipe is inserted in the middle of an existing pipe, new junction, Does the existing pipe need to be redefined into two new pipes, each connected to the new junction, or how would this work?
Yes, that's exactly how it would work. I'm not sure if there already is a quality of life function for that. I think there is definitely like a pull request if you know what that is. So somebody already developed it, but it's not in the main repository yet. But yeah, that's something I already used. Like if you split up a pipe, you basically need to redefine two new ones that connect to this new junction and delete the old one. But yeah, this can be done more or less automatically. So you uh, take the same parameters of the old pipe for the new ones, and yeah.
Thank you. Then we have another question by Enea, and I will merge the two questions actually by Enea. So, does pandapipes work for multi-rings networks or just for branched networks? And also, how did you verify your solutions and which benchmarks have you used? Did you validate your model on the Open DHN benchmark? And if yes, how did it perform?
So yes, you can model branched as well as looped or meshed grids. And I think the second question is to Hyacinthe model.
Yeah, I'm not sure. It may be. So the Milan network, the one that I show is actually a mesh network. So yeah, pandapipes can manage them fine. Um, there are some constraints still that you have to make sure that you can define correctly your network in order to pandapipe to find out the mass flow that goes through each of the part of the network. But yeah, in general, you can do it. Did you verify session with benchmark views? I don't know about OpenDHN benchmark actually, so no, I didn't use it. If yes, it performed, so no, actually I didn't. On the Milan network, I had a few data on the, especially so on the part of the Canavese power plants. But on the network overall, I had only a few data on, I think one of the substations that is pretty far from the network. And so I use this one as a main reference. But I don't have enough data on the overall network in order to make a check of like the state of the whole network.
Thank you so much, Hyacinthe. So last question by an anonymous attendee. Is it possible to simulate networks that have producers or consumers working on different temperatures, but with a common return pipe? Example, 95 Celsius degrees or 80 Celsius degrees and common return at 45 Celsius degrees. And also, how do you generate load profiles for the consumers?
So yeah, the first question, yeah, it's possibly possible. It's I mean, Hyacinthe kind of showed it on his slide. You can use a predefined component we have for that, the heat consumer, where you can define. It was not shown on the slide, but you can also define instead of a temperature difference, a set return temperature, and then if you have different loads and but set the return temperature to for example 45 degrees for all consumers, you basically let pandapipes calculate which mass flow is then used to achieve this 45 degrees in the return, depending on what the different consumers need. So if they have different flow temperatures like 95 or 80 degrees. Yeah. And for the load
Oh yeah,
profiles,
the last
maybe
one.
you want to answer? Yeah.
generate load profiles to consumers. In this case, I use a simple, I had only like one data from one mass flow meter actually in one spot of the network. And so I use this one to generate a load profile that I apply to every consumer, which is probably not the perfect way to do it because of course they all have their different loads habits and profiles. So it would be actually very easy to use pandapipes with, for example, load forecasting algorithm. If you have a demand forecasting from, for example, temperature data, it could be easy to create a controller to put this data inside the model. But in this case, it was not used. Yeah, I can show the question. And
I think that's all for the QA session. We're heading towards the end. So I want to thank again everyone that, all of the speakers from Erik to Hyacinthe to Renato today. Let me remind you once again that I hope to see you, all of the attendees, in the next meeting for the Panda prosumer in a month from now. Also, I would like to remember that all the participants will receive soon the slides from this webinar. And also that the video will be, has been recorded and will be uploaded on YouTube by the EHP, on the EHP channel. And that's all for this second webinar of the Synergy Nets webinar series. Thank you all, and I hope you have a good rest of the day. Thank you so much, everyone.